Hello, and welcome to the lecture on Chapter 4 from Astronomy Today. We're talking about spectroscopy this time. This is the study of light, and this lecture is very much a continuation of the ideas we saw in the last chapter, which was Chapter 3. So please remember to watch that video before you watch this one. In that lecture and in that chapter, I talk about radiation, which is light, which comes from the acceleration of charged particles. So remember that idea, okay? All right, so our goals for this lecture are to talk about spectral lines, atoms and radiation, okay, that's part of where light comes from, including the hydrogen atom specifically. Then we'll talk about the formation of spectral lines, why light is a particle and how we know it's a particle, how that relates to the light that's produced by molecules, which ties in a bit with Chapter 3, and spectral line analysis, which also will harken back to Chapter 3, as well as touch on the new material. Okay. So if we're talking about spectroscopy, then there might be something that is a spectroscope, the device that does spectroscopy. Well, there is, okay? And there's a number of ways to build one, but the best is a prism, all right? A prism bends light through the property of refraction, which is the bending of light, and different color lights bend differently, and that means that those different color beams of light will then get spread apart through a process known as dispersion. That spread apart light gives you a spectrum right there. In this case, a full rainbow spectrum from blue to red, okay? And that's because the light, in this case the red light and the blue light on either extreme ends of the rainbow, got bent differently, thus got spread apart, and then refocused with this lens onto the screen, okay? And this is from a hot bulb, which is a hot solid material. This is creating a continuous spectrum, a rainbow spectrum. Continuous spectrums are what we talked about before when we talked about Wien's law. So please review Wien's law, which is in Chapter 3. Okay, I'll mention it one more time in this lecture. Okay, so that's a continuous spectrum from a hot solid. But what about the spectrum? Spectrum, again, just is referring to this effect that we see on the screen, the spreading out of the light. So what about the spectrum from a heated hydrogen gas? So this is a very different example of a hot solid, okay? Instead, we have a gas. Gases have very different properties. There are many less atoms per cubic centimeter in the gas than the solid. Very different phenomenon. Well, in this case, we have the light go through the prism, the light gets spread apart, but what we get is not a full continuous spectrum, not a rainbow, but instead a few distinct lines. We call these emission lines. So to be clear, a full rainbow is a type of spectrum. A series of distinct emission lines is also a type of spectrum, okay? So these are both spectrums. The difference is that one is lines and the other is continuous. We would also say that these are both created by emission. Emission because they both came from a source of light. In one case, a hot solid, in the other case, a hot gas, okay? So to be clear on our terms there, all right? So there we have our first example of emission lines. Now, emission lines are different for different elements. They can be used to identify the elements. They're the fingerprint, just like people have distinct fingerprints, atoms have distinct fingerprints, but they take the form in reality of spectral lines. Hydrogen has a very simple spectrum line, all right? It has a very simple emission spectrum, and I guess it would be a set of spectral lines. Why would hydrogen have such a simple set of spectral lines? Because it is the simplest atom. It's just a single proton surrounded by a single electron. Okay, that's it. So it's the simplest atom in existence in the universe, and it has the simplest set of emission spectrums. Other examples are sodium, helium, neon, and mercury, to name just a few on the periodic table that can create spectral lines like this, emission spectra. Basically anything that can become a gas and can be isolated by itself could create nice sets of lines like this, okay? Notice that this is all in the visible spectrum, between about 650 to 350 nanometers. Remember, where the visible spectrum falls on the overall electromagnetic spectrum. We're going to focus largely on the visible today, although it will touch on other parts of the spectrum, including UV, infrared, and radio. So there's another type of spectral analysis, another type of spectral line set that can form, and these are absorption spectrum. And they are, you can think of them as the opposite of the emission spectrum. What happens in this case is we have a hot solid, like the light bulb, a cool gas in front of the hot solid, and the prism on the other side. In this case, the light from the hot solid must pass through the gas. The gas then absorbs some of the light in the same way that its fingerprint would show up if it was the source of light. So we have absorption lines, which are gaps in the rainbow. See, is a full continuous rainbow spectrum, but with a few gaps. And the location of those gaps, you guessed it, are the exact same locations where the emission bright lines would be for the element. Okay, so this element could be hydrogen and it would have those distinct lines in the same place, but here they're black lines instead of colored lines because they have absorbed the light, see, instead of creating it. Absorb the light from the hot solid. Okay? An absorption spectrum can also be used to identify elements because again, it's the same fingerprint. Okay? And this is showing emission to absorption. They match up perfectly. Okay, so Kirchhoff's laws of spectral lines, or Kirchhoff's laws of light, I mentioned that because there's actually another well-known set of Kirchhoff's laws that apply to circuits in physics, totally separate field or subfield, but the same name, okay? So not to be confused with Kirchhoff's laws of circuits, these are Kirchhoff's laws of light, if you were to Google them. Well, those laws say that luminous solids, liquids, or dense gases produce continuous spectrums. All right, those are the type that we can use Wien's law with. Okay, see Chapter 3 and the lecture for Chapter 3. Those are the continuous spectrums, the rainbows that I've mentioned many times. Okay, see I was leading up to these laws. Low density hot gases produce emission spectrums, the fingerprint of the element. Continuous spectrums incident on cool thin gas produce absorption spectrums. So these three laws apply to these three statements, okay? Here are Kirchhoff's laws illustrated, a good summary of all the ideas that I've talked about. It's a good reference slide that you can refer back to make sure that you understand the three and otherwise fill in your gaps of knowledge. Okay, so the existence of these spectral lines begs a question. Where are they coming from? Because if continuous spectrums, like from a dense gas like a star, essentially a solid, if that emission looks like a rainbow, has a peak that corresponds to a particular color according to Wien's law, if all that's the case, then we say that that light comes from the source of all radiation, the acceleration of charged particles, because there's a lot of hot charged particles bouncing around on the surface of a star, producing light. But what about these cases of a single element producing light? Why are the colors so well defined? Why do they just come in distinct bands? It can't just be electrons randomly bouncing around, otherwise they would produce all colors like a rainbow. So what is restricting the motion of electrons? How do we even understand something like that? Well, that leads to the Bohr model and the birth of a subfield of physics known as quantum mechanics, which we won't get into that much today. But we do want to understand that this idea of distinct spectral lines applies to distinct energy transitions of the electrons in an atom, all right? And these are known as allowed orbits for the electrons. Example, we have an electron that's in the ground state. This is the least energy that an electron can have inside of an atom. This electron then is going to become excited because the input of energy allowed for the excitation of the electron. When it does that, it takes a larger orbit, okay, a more excited orbit. It's further away. This electron then can later relax, returning to the lower orbit, which effectively means that it returns to this state. When it does that, it emits light. And I'll say this again, we have slides that show this idea in just a moment, but that's the key idea. We have allowed orbits, nothing in between is allowed. That means that the energy of the light that's produced exactly matches the very restrictive energy step that the electron can take. That idea of stepping energies is the Bohr model, is what is known as quantum mechanics, because a quanta is a step. So quantum mechanics is the study of steps, distinct steps in the physics of very small things. Now, a modern understanding of the model of an atom, and this is, by the way, a hydrogen atom, as can be seen by having only a single proton and a single electron, H representing hydrogen. Well, the more modern model of the atom involves orbits that are allowed, okay, but they're not quite orbits anymore, they're clouds. And they're clouds because they are probabilistic. And this gets into some of the really interesting ideas about quantum mechanics and why people talk about quantum coding and quantum computing, and it is supposedly very complicated, and that has to do with its probabilistic nature. It also has to do with something that you may have heard of, known as Heisenberg's uncertainty principle. Again, we will not touch on it here. So more about the allowed energy states. Well, it turns out that the model for hydrogen, although it is not completely accurate, is quite close to being accurate and is very, very simple, because there's a very simple equation to represent the energy levels of the electron. So if we have an energy in the lowest electron in the lowest energy state, the ground state, then it would have an energy using this equation right here, where n equals 1, as we can see labeled in the figure. So all I would do is plug in a value of 1 for n, and then calculate the energy of that state. That energy would be in electron volts, and an electron volt is 1.6 times 10 to the negative 19 joules, where joules are a standard unit of energy. So in other words, it's a very small chunk of energy that is traditionally measured in electron volts, so we don't have to put everything in scientific notation. 13.6 is just a number that's specific to hydrogen. It's just scientists' best guess, not really based on principles of the model, and that's why it's been improved upon in the almost 100 years since this model was first proposed. But again, it's fairly accurate, and that's why we continue to use it today, okay? And if we wanted to find the energy of the next lowest energy state, which is the first excited state, we would just plug in n of 2 instead, or n of 3 if we wanted to find the energy of the next state. And you can see that this figure actually shows those example energies. It shows 0 electron volts and then 10.2. Well, why 0? Because, well, that's the ground state. 10.2 because you've got up a step of 10.2. You could find that by just calculating the difference between plugging in 2 and plugging in 1 respectively, and subtracting E2 from E1. Okay? That will give you the energy difference of 10.2. So you can actually easily calculate these energy differences. And I want us to hold on to this formula of expressing energy, because we can later relate this exact formula to another simple energy formula, but that a formula instead representing the energies of light particles known as photons as a function of frequency. And that will really complete the quantitative part of the chapter. But let's move on for now, because we'll get back to that. All right? So quick little discovery note here. Since we are about to start talking about light as a particle, and then tie that back in with the hydrogen atom, the Bohr model of the hydrogen atom, we need to justify that light is a particle. Because in chapter 3, I made a big deal about light being a wave, which it absolutely is a wave. But light is also a particle. Well, why is that? Well, that's because light has a duality that isn't quite like macroscopic things, like even molecules or large solids. Instead, light behaves very differently in a way that is maybe hard for our language to comprehend. But the proof of light as a particle was done in an experiment known as the photoelectric effect. This effect or experiment consists of shining light on a metal, which allows electrons to be emitted from the metal. The metal becomes hot and it emits electrons. They get freed away with a lot of energy. The frequency must be higher than a minimum characteristic of the metal. The metal holds on to electrons in a certain way dependent on what metal you're talking about, whether it's copper or steel or iron or whatever. The increased frequency, the more energetic the electrons. The increased intensity means more electrons, but the same energy. So why is that? Well, here is a picture of it, of the photoelectric effect, and a note that it can only be understood if light behaves as a particle. In other words, this result of the experiment wouldn't make sense if light was only a wave. And why is that? Well, check it out. We've got infrared light and we've got red light. Well, these correspond to low frequency, long wavelength, okay? Now, of course, not low frequency compared to a radio wave or long wavelength compared to a radio wave, but compared to other types of visible light or near visible light. Okay, so this is our low frequency light. Well, it turns out that that light will never emit electrons. No electrons will ever come out, no matter how bright we make the light. Now, if light was behaving like a wave, then the wave should get absorbed by the metal, and the bigger amplitude the wave, or the more waves, then the metal will eventually become hot enough that it'll start to free electrons. But that never happens. So why is that? How could that possibly be the case? Well, that could only be the case if light is not behaving like a wave when it interacts with the solid of the metal, but is instead behaving like a single barrage of particles, or a barrage of single particles. So many individual packets of light. Because then we see, if we change the light to blue light, now each of these individual packets of light, known as a photon, each individually have a lot of energy, enough energy to crash into an electron in the metal and actually bounce it out, just like billiard balls bouncing on a pool table and one ricocheting after the shot. In this case, the electron ricochets when it gets crashed into by the photon. That's not a wave-like behavior. And furthermore, the blue light can be very dim, but since it's still composed of individual high-energy photons, it will still liberate electrons, just fewer of them. So that type of behavior, again, can only be understood if light is behaving as a particle, not as a wave. So if light is a particle, then each particle of light has a certain amount of energy, expressed by this formula, E equals hf. This is the energy of individual photons, all right? So the energy of particle of light. Now, just to be clear on that word particle, because I use it a lot as a physics professor, well, I want to make sure you understand it. Because when I talk about electrons, that's a particle, very simple chunk of matter. When I talk about photons, which are the particles of light, that's also a particle. So that means that particles interact together. Particles have a lot in common, whether they're electrons or photons. And that's why this story makes sense. This model of the universe makes sense, because we have electrons inside of an atom, a tiny little particle. We have a photon coming in, another tiny little particle, and they interact because particles interact with each other. Okay, well, this is the energy of a photon. H here is a constant of the universe, one of 3 fundamental constants, and it is expressed as 6.63 times 10 to the negative 34 joule seconds. Incidentally, the units of angular momentum, which is neither here nor there. But that is a very small number, and it has to do with that quantization, that stepping of the tiny world. Well, this is kind of the scale at which tiny steps are made. Okay, so let's then look at this. This is our energy formula, but it's not the first one, right? This is the energy of a photon of light. This formula is the energy between electron excitation levels in the hydrogen atom. Well, you guessed it, we can set these two energies equal to each other. And we can solve for an unknown frequency. We could solve for an unknown n value, which represents the orbit number of the electron. See? And it's all about setting the photon energy equal to the electron energy. Okay, all right. So let's now finish up our last few topics of the lecture. The formation of spectral lines, all right? Well, absorption can boost an electron to the second or higher excited states. There are ways to decay. So if an electron gets excited to a higher state, it can decay directly back to where it started. So for example, flipping back to here, I could have an electron in the ground state. It could go all the way up to the 4th state, and then after it stays there for a moment, usually a tiny fraction of a second, like a billionth of a second, then the electron comes back down to the ground state, and then it releases a photon, okay, particle of light, which is the same exact one as absorbed. So it kind of took that photon in, that photon became the orbital energy of the electron, then the electron relaxed and released an identical photon. But it doesn't have to be identical, because instead the electron can cascade down. It could take a step down to n equals 3, and then to n equals 2, and finally back to n equals 0. Okay? So here is another picture to show it. I didn't want to give it away right away. This is direct decay. So direct decay is exactly like I showed. Zoom in a bit. We have a low energy UV photon, low on the UV spectrum. It comes in, crashes into an electron that's in the ground state. The electron gets excited to the second state, the n equals 2, which is the first excited state. All right, so it gets up there, and then it relaxes back down, and it releases the exact same wavelength as well as frequency light particle that it absorbed, right? See, they're the identical particle represented by the same color, all right? And there was actually no choice, there was no possible cascade because the initial absorption only led to an energy change of 1. It didn't go up 2 steps. If you don't go up 2 steps, you can't take 1 step at a time down because there's a total of only 1 step to take. Well, what if we have a higher energy UV photon? So still in the UV part of the spectrum, but a little bit more energetic, represented by purple in this case, you can see, blue and purple. All right, so the purple UV photon comes in here, crashes into the electron in the ground state, causing it to jump up to n equals 3 instead. Well, now there's 2 options. It could decay all the way back down, so decaying or relaxing, which are 2 synonyms for the same process in terms of the electron, all the way back down in the ground state, or it can take those incremental steps, taking a smaller step, which releases a lower energy visible photon, and then finally releasing a UV photon identical to the one in the first example. Got it? Cool. Okay, so that's an example of direct decay and cascading decay for an excited electron around the nucleus of an atom. Okay, in this case, again, we're assuming it's all really hydrogen because we keep showing 1 proton and 1 electron. Well, the absorption spectrum is created when atoms absorb photons of the right energy for excitation. All right, so it's basically just the absorption part, like shown in this step right here. Okay, so that's where you get the idea of those black lines in the otherwise continuous spectrum. Other types of spectrum include multi-electron atoms. These are much more complicated spectra, many more possible states. Even when we go up to the next simplest element on the periodic table, helium, would you think, oh, well, that's only 2 protons and 2 electrons. It can't be that much more complicated than hydrogen, which is 1 proton and 1 electron. Well, it turns out it is quite a bit more complicated. So it's such a dramatic step. And then as we go on to the next elements in the periodic table, it just gets increasingly complicated, even for otherwise known as small elements, all right? The oxygens, the lithiums, the borons, these other light elements on the periodic table. Much more complicated than hydrogen, but they do still have spectral bands, which we saw way back when we saw the spectral bands of even things like mercury and neon, which are pure elements. But they have so many more energy levels, so much more harder to calculate. You would never see a simple formula like the simple formula you saw for the Bohr model of hydrogen. Okay. There's also ionization, which changes the energy levels. That's where a atom, such as maybe helium or something larger, say carbon, has permanently lost some of its ions. It's become an ion. It has permanently lost some of its electrons, and in doing so, it's still effectively that element, but now it's a ionized form of that element. Okay. All right. Now, interesting thing about emission lines in the real world is they look messy like this one, and they're often composed of many elements because most clouds of gas in outer space aren't pure something. Even if they're mostly pure hydrogen, there'll be trace amounts of other elements. So here we see an example of a nebula or gas cloud in outer space that includes a lot of hydrogen, as shown by the big spike, but also helium and neon and others. Maybe other types of helium or another part of the spectrum of helium, but it could be ionized helium. Also includes oxygen, more telltale lines of hydrogen, and so on. All right, so it's quite a process to take something messy like this and analyze it. Okay. Molecules also produce spectra, and the individual atoms within the molecule absolutely have electron transitions, as we've spoke about. Okay. But they can also quantize energy in 2 other ways. They can have vibrations, where a faster vibration can become a slower vibration and release a photon of an exact wavelength that matches the energy difference, delta energy, between those 2 vibrational levels, those quantized vibrational levels, and even rotation itself is quantized and will emit light. In general, for hot gases, but not extremely hot gases, vibrational transitions correspond to infrared because it's lower energy, all right, but not that low. And rotational transitions are very low energy, so they correspond to radio waves. Because the longer the wavelength, the lower the energy, thus the lower the energy, the quantized motion, okay? Molecular spectra are much more complex than atomic spectra. This is actually a wonderful example. This is just comparing molecular hydrogen to atomic hydrogen. You might wonder what's molecular hydrogen. It's actually the more common form of hydrogen, and that's H2. So it's two hydrogen atoms together. Well, look at the difference. H2 almost looks like a rainbow with kind of a lack of a lot of green lines, but many, many spectral lines. Compare that to just H, and dramatic difference. Just that single bond between atoms produces so many different quantized levels of motion, because once it becomes something like this, once we have, this is of course carbon and oxygen, but once we just have two H's, then think, now what can you do? You can rotate, you can vibrate, all that motion corresponds to different energies, okay? So the information that can be gleaned from spectral lines include chemical composition, as we spoke about, taking a messy overall pattern like this and identifying individual elements within, okay? It can identify temperature, okay, but usually only continuous spectra, like the ones that we use of Wien's law, because of course Wien's law is what we're referring to here, okay? It can also determine radial velocity, how fast something's spinning, okay? Now, it can also directly relate to translational velocity, which would be motion away or towards the observer. We talked about that when we talked about the Doppler effect. Here's an example of the spectral lines of hydrogen for a hydrogen gas that's at rest, one that is moving away from us at 300 kilometers per second, and one that's approaching us at 600 kilometers per second. When something is moving away, the red becomes redder. That's the red shift, okay, because motion away. If the gas is moving towards us, then we get a blue shift. The red is less red, okay? The bluers are bluer, okay? Line broadening can be due to a variety of causes, okay? Now again, notice this is not a spectral line set, but instead is a continuous spectrum. And that's to just make a point about broadening. So think of this as kind of a tie-in with spectral lines in general, or spectroscopy in general, but less about spectral lines and more about continuous spectral curves like the rainbow spectrums that we discussed for Wien's law, okay? Well, line broadening can be due to temperature, so it can certainly affect the broadening effect as we see here, all right? Because that's because the Doppler shift of all those individual atoms means that some are moving away from us, some are moving towards us, and that means that the red parts become redder and the blue parts become bluer, and the overall effect is that continuous spectrum spreads out, it becomes broader. But what's interesting is that broadening, in addition to being due to thermal effects, which is temperature, of course, can also be due to motion. Because if an object is spinning, and here obviously we're talking about a solid, not a gas, but if a solid is spinning, then we have a broadening because sometimes there's atoms moving towards us, which have a blue shift. Sometimes there's atoms moving away from us, which have a red shift. That overall effect of all those lines layered on top of each other, the light that we observe shine through a prism and then focus on a screen, means that we get a broadening of what would otherwise be this spectral curve, becomes this much broader spectral curve, okay? So let's summarize now, okay? So what we talked about in this chapter included kind of an introduction to how we split up light, then a lot about quantized energy levels of the hydrogen atom and photons themselves, even a justification of why photons are a particle with a photoelectric effect. But then we kind of tied it together with an overall discussion of spectral curves at the end, okay? So just a big picture there, but let's hit the bullet points here. So we talked about how spectroscopes split light beams into component frequencies. We talked about how the continuous spectrum is emitted by solids, liquids, and dense gases. That was one of Kirchhoff's laws. We talked about how hot gases have characteristic emission spectrums, okay? We talked about how continuous spectrums incident on cool, thin gases give characteristic absorption spectrums. So these are the three types: continuous, emission, and absorption. All right, then we talked about how spectra can be explained using atomic models with electrons occupying specific orbitals. This was most relevant to, here we go, most relevant to emission spectra, right? This idea of the allowed orbits, occupying specific orbits, okay? All right. Also applies to a lesser extent to absorption lines. All right. Emission and absorption lines result from transitions between orbitals. Okay. Molecules can also emit and absorb radiation, making transitions, which will make defined lines as well, but there'll be many more of them, including ones from vibrational and rotational states of molecules. All right. And that's it. Okay. So I hope that this lecture has been interesting and informative. Thank you so much for watching.